In order for you to understand horizontal shifting better, I have an example here of sine theta minus 45 degrees versus the regular or a mother graph sine theta, y equal to sine theta, which is the green one here. I also, because I'm subtracting 45 degrees, I've calibrated my horizontal axis to include the values of 45. So the scale here is each 45 degrees. So, and then also included this table here where I've put some regular values, like for instance minus 180, minus 90, 0, etc. And also we know from the special triangle, the isosceles triangle, that we find sine of 45 degrees is 1 over square root of 2, which gives you that 0.71 approximately. On this graph we cannot draw as accurate as 0.71, so it's just an estimate, but the graph here is drawn by GeoGebra, which can draw it accurately. Good, so let's look at certain points. If I, for instance, start here at 135 degrees, so this is my theta value. If I now subtract 45 degrees, then I will get 180 degrees, like that. But at 180 degrees, I will have a value of 0 degrees, so that value must go in here. I'm going to leave some space in between the values so that it's easier to see, that it's not as cluttered. So if I look at minus 45 degrees, then if I add 45 or subtract 45 degrees, I get to minus 90 degrees. So from there to there, I get minus 90 degrees. So I have to pick my value there, and then I will put it in here at minus 45. If I look at 45 degrees and I subtract 45 degrees, I get 0 degrees. That means I will pick the value here for the regular sine theta of 0 degrees, so that gives me 0. And so will also this 0.7 minus 0.7, and this is minus 0.7, etc. And we can see, I'm just going to pick another color. We can see now that these values are now from there to there shifted 1 unit to the right, and that one is shifted 1 unit to the right, and that one is shifted 1 unit to the right, and so it will happen for each and every value. So if I subtract minus 45 from the original theta, it means that my graph will shift to the right. So let us look now at when I have theta plus 45. So I'm just going to move to that side now to explain that. So if I take, for instance, 135 degrees and I add 45 degrees, then I will get at 180 degrees. But that is the same value as the 0 there, so it means I must plug in that 0 value here for 135 degrees. If I look at 2 to 5 and I add 45, I will get at 270 degrees, but that happened there, so I must put that value here, which is minus 1. So in the same for 360 degrees, if I add 45 degrees, I'm now out of the interval. We can do it with 315. So let us do 315. If I do 315 and I add 45, I get 360 degrees. So I must read it off at 0, so that value should be plugged in here. And the same with the 0.7, and again that one is minus 0.7. And I'm just going to change the color so that I can show you the direction that it's moving. So if you look at these values, all of them moved 1 unit to the left. So in general, I can say that if I say minus 45 degrees, then everything moves to the right. And if I have plus 45 degrees, then everything moves to the left. And I hope the graph or the table here helps you to see that. If you look at the graph here, we see if I take my original function 90 degrees, so everything moved to the right here. That goes there, that one goes there, etc. So every value moves 45 degrees to the right, and then I get my new function. On this page, I just joined all the dots that we made on the previous page. And now we have the blue graph here, which is, if I measure here, I see the distance between the graphs horizontally is 45 degrees. You can see it from the graph, 45 degrees. So, in which case, the blue graph is the green graph shifted 45 units to the right. You will see that the period is still 360 degrees. The amplitude is still 1. The roots, previously we had the roots at theta equal to k times 300, k times 180 degrees. We case an element of z. Previously we had the roots at theta equal to k times 180 degrees. We case an element of z. But now, these values moved 45 to the right, so we will just have 45 degrees plus that. So if I take my first value, where k is equal to, so this minus 45 here becomes a plus 45 there. So if k is equal to 0, then I'll get my first root, which is at j. This is when k is equal to 0. When k is equal to 1, I will get 45 plus 180, which gives me the value at L. This is when k is equal to 1, etc. You can check all the roots like that. In general, the formula for the roots are what we wrote there, so we can write theta is equal to plus 45 plus k times 180 degrees, where k is an element of z. The extremes are still minus y equal to minus 1, y equal to plus 1, but now the minima, previously we had the minima at y equal to minus 90 degrees plus k. I'm just going to move it up a little bit, plus k times 360 degrees, where k is an element of z, because if I take b here and I add 360 degrees, then I will end up at f there. But now the minimum has also shifted 45 degrees. So that gives us minus 45 degrees plus k times 360 degrees, where k is an element of z. The same for the maxima. We have y equal to, we can just start with the first value here, which is actually 90 degrees plus 45 degrees plus k times 360 degrees, where k is an element of z. So that gives us 135 degrees plus k times 360 degrees, k element of z. So on the next page is just a summary of what we said here, and you can read through the page so that you can make that you are certain of what's happening when we say minus 45 there. Remember what happened in a table, and then what's very important is that you know that the graph shifts to the right with 45 degrees. Good, and that is horizontal shifting. So this is now an easy one, and you can on this graph now draw the graph of y equal to sine theta plus 45 degrees to verify that you understand